We're recording now. So here's another linearization problem. Another example of something that I did yesterday. What else did I say for the cosine sine function? So it says find the linearization, and what that means is turning the curve into a line. That's why it's called linearization of f of x equals cosine x at x equals, that's an t, I don't know, x equals pi over 2, and use it to approximate cosine of 1.75. Why would you ever want to do that? Yes, sir.
I just have a quick question. How is this any different than just finding the equation of a tangent line?
So
just turning a curve into a line, isn't that same?
Yeah, but you're using that line to approximate values of the function. Okay, so with a tangent line, you're just we found the equation of the tangent line. What is the rate of change at that specific point? This is, okay, if I go a certain distance away from that point, but close to that point, okay, I can use the tangent line to approximate values of the function. Okay, so I think you'll see in this example what I should. So it's the same, but it's different. So y equals cosine x, you should know, kind of looks like this, right? It goes like this. And at pi over 2, it goes through 0. Right? You guys know that? And so if I were to draw the tangent line right there, it would look something like that. All right? So I know that the cosine of pi over 2 is what? You guys know what the cosine? Yeah, you do. What's the cosine pi over 2? 0. Okay? In this case, what I'm going to use the tangent line at the point pi over 2, which isn't 1.75. It's pretty close to 1.7 because pi over 2, like pi is 3.14. So pi over 2 would be like 1.66 or something like that. Okay. So what I'm trying to do is use this tangent line to approximate the value of 1.7 cosine of 1.75. Okay. And to do that, I'm going to use not the tangent line at 1.75, but the tangent line at pi over 2. Okay. And so yeah, today you could just plug that in your calculator and get it done. But maybe back in the olden days they didn't have calculators, and so they would actually have to as part of the calculus, to approximate the curve with the tangent line. And so what we learned yesterday is that L of x, the linearization function, is equal to f of a plus f prime of a, which is the slope of the tangent line at that point, times x minus a. Right? Remember that? And so now what you're going to do, you're going to plug in at pi over 2. So I can find f of a. What's f of pi over 2? A is pi over 2 in this case. So a, 0. So f of pi over 2 is 0. And then I need to find f prime of a, which is f prime of x is equal to the derivative of cosine of x. So what's the derivative of cosine of x? Negative sine of x. And then I am going to plug in pi over 2 in there. Alright? So I'm going to take, so f prime of a is equal to f prime of negative sine of x. What's sine of pi over 2? 1. And so that becomes negative 1. So that is this value right here, negative 1, and a is just pi over 2. So L of x looks like f of a, which is 0, plus f prime of a, which is negative 1, times negative 1, times, I'm just going to say minus 1 times x minus a, which is pi over 2. And if I simplify this expression, I just get negative x plus pi over 2. So what this linearization idea says is that if I take a number that has a plus sign, does that look like a t? Plus sign. So if I take a number close to pi over 2, and I want to find the cosine of it, I could just use this line. So I could kind of do that in my head. Okay, so L of 1.75, okay, is going to be equal to negative 1.75 plus pi over 2. So if I do that on my calculator, watch, if I do that on my calculator, so if I go negative 1.75 plus pi divided by 2, okay, I get out this number, negative 1.792. So what that's saying is, using this curve right here, if I go 1.75, I think that'd be slightly in front of pi over 2, right? Then the value on the tangent line is negative 1.79203. So to see how close I am, I could actually use my calculator to find the cosine of 1.75, because that's what I'm trying to do. I'm trying to use the tangent line to approximate the value of the function. And if I do that, you see that those two numbers are very close together. This is an estimation for the value using the tangent line. This is the actual value if you were to use a function instead. You follow that? Why would you want to do that? I guess because it's easier to plug into a line than it is to take the cosine of something, especially if you don't have like a calculator or something like that. Okay? And it has some applications in real life. All right. So, yes, Caroline.
So for this problem, we use allowed.
So the other thing that I didn't teach you yesterday, and the other thing that I didn't teach you yesterday is, no, I'm doing fine. I need a blank page. Is that approximating binomial powers. And there's a formula that comes up out of the first example that we did, approximating binomial powers. And I don't know if you would see this on an AP test, I really don't know, but there's this formula that for small values of x, for small values of x, remember that one where yesterday we did the square root of 1.01 or something like that? This formula comes out of that idea. 1 plus x raised to the k power is very close to 1 plus k times x. For example, if I want to find, whoops, that's wrong, that should be an x, this should have looked like that. Okay? So, for example, if I want to find 1 plus 0.01 raised to the 5th power, that would be very close to 1 plus 5 times 0.01. Okay? So it would be very close to that. And that's just something that falls out of finding the equation of the tangent line and then plugging in a value. So another more complicated example, they might say approximates the cube roots of 1 minus x. So in order for you to be able to use this formula, this number right here needs to be a 1. Okay? You remember we were talking about that yesterday? in order for you to use this formula, this number here needs to be a 1. And so approximate the value of that, and then use it to approximate, let's make one up. The cube root of, use it to approximate the cube root of, say, 0.97. Alright? Yes, sir.
So if it's not a 1, does it not apply, or do you have to?
Yeah, if it's not a 1, this formula doesn't work. Then you have to... Yeah, that's what I'm going to do. So first we're just going to find the equation. So this is this is equal to, first you want to rewrite it in this form. So it's 1 minus x raised to the k. So I could rewrite this. This is approximately equal to 1 minus, 1 minus x raised to 3. So this is approximately equal to 1 minus 3 times x. You're not finding the derivative or anything. Your linear...
Those two things are not...
What? I'm sorry. 1/3. Okay? Sorry. 1/3x. Like that. Okay? Now, I'm going to plug in. So, this is about equal to, this is equal to the cube root of 1 minus what? 0.03. Alright? So I could use this linearization of this function to approximate this cube root. So it's 1 minus 1/3 times, and I made this one up, 0.03. So 1/3, what's 1/3 of 0.03? Is that 0.01?
Yeah.
Yeah? Is it 0.01? So that would be 1 minus 0.01, which would be equal to 0.99. So let's see how close we got. Alright? So if I take my calculator and use the cube root, math, cube root of 0.97, and I hit enter, I get very close to 0.99, don't I? Okay? 0.989, so I'm off by about 2/1000 or something like that, right? Because if I change this to a 2, it would go, everything would bounce up. So I'm really close. Oh, I wrote 0.09, but I meant 0.01. Yeah. Good. Don't listen to what I write. Listen. Maybe something. Okay, so that's what approximating using the linearization. So if you had a function like this, 1/1 minus x, you could write this as 1 minus x raised to the -1. And so the linearization of that would look like 1 plus x. I'm just doing another little side example. So if I had something like this, I could rewrite this as this is the power to the -1. And then I could rewrite this, I just take this exponent and bring it in front of the x. And so if I want to approximate, say, 1/1 minus 0.99 or something like that, then I could, wait, 1 minus 0.01. If I want to do 0.99, I would do it like that. And I could use this formula here to find the approximate value of 1/0.99. Anyway, I don't want to get
How
you.
close do the numbers have to be to like do this? Like
How close do you need to be to that number?
Yeah, would that be like 0.05 or whatever?
Yeah, great. So these are only going to work for numbers close to 1, right?
Okay.
Yeah. But for the other linearization, you want to be within, I would say, at least a 10, probably 100, or some. But the closer you are to that value, the more precise the tangent line is. The other thing, the steeper the tangent line is at that point, the less accurate it's going to be, right? If I go over a little way, All right, yes, sir.
What would you do if you had something like 4 plus 3x?
So if I had 4 plus 3, what do you mean?
4 plus 3x, how do you apply that?
Well, first of all, that's just going to make a line, so I don't have to use the graph. But if you had like 4 plus 3x squares or something like that, you would, so maybe you want to find then you'd have to actually find the equation of the tangent line and use the linearization of that tangent line, right? Because it's the sign of
How do you go from 1 minus 1/3 x over equals to, how do you go
from here to here?
Yeah.
Because, well, first I rewrote this as this, right? And then I used this formula where I just bring the exponent in front of the variable part. Okay?
Yeah.
So that becomes 1 minus 1/3 x. And then in here, I plug, since 0.97 is like 1 minus 0.03, my x is 0.03. Yeah.
To clarify what I was asking, it's actually 4 plus 3x all raised to 1.
4 plus 3x all raised to the 1/3, and they say find the linearization of that function.
Yeah, with what we just talked about.
I don't think you could do it with what we just talked about.
Yeah.
You have to find the equation of the tangent line first. Okay? So you couldn't just use that 1 plus 1/3. I don't think it works. I don't think you could write it as 4 plus 1/3 times 3x. I don't think that works. Okay? So you would actually just come up with the derivative and then find the equation of the tangent line. Okay? So, next thing we got to talk about is differentials. I got to go faster. Differentials. Okay? And differentials is how much y is changing as x is changing by a certain amount at a certain point. Okay? So we have just written, so when you write this dy dx equals something, that means the instantaneous rate of change of y with respect to x. Right? Well, it happens to work, so this we wrote as f prime, that's equal to f prime of x. So it works, and they proved, I guess, algebraically, that you can actually separate these things and treat them as if they were actual quantities. So I could rewrite dy equals f prime of x dx. Okay? Or sometimes they'll write, this is an equivalent statement, df is equal to d of f of d of f dx means the derivative of f times dx. In any case, I'm gonna erase this because that's kind of confusing. In any case, what this means as x, if you plug in some point, say like 3, and you want to go away from 3 a certain amount, like 0.02, dy is the amount that y would change if you move this far away from x. Okay? And what you're doing, you're using the tangent line to approximate that change. Let me just give you an example, and then maybe it will make sense.
Crazy, man.
Who's crazy?
So y, the dy is the amount that y changes.
Yeah.
So that is to the next.
Right. Good. So find the difference. So here's an example. Find a differential. I don't like the one they use. Differential dy if f of x is equal to x to the fifth, I'm not sure why they use this crazy example, x to the fifth plus 37x, when x equals 1 and dx equals 0.01. So what this means graphically is, come on, shush. So this is a fifth degree function. If I plug in 1 in here, what do I get out? What do I get out? I get out 38, right? Which is kind of ugly, but I'm going to pretend I don't know what this function looks like. I know it comes from the bottom, and it goes up to the top somewhere. Maybe it's going like this or something, but let's say that this is the point. It wouldn't be there, would it? It'd be somewhere over here. But let's pretend that this is the point 1 comma 38. So what they're doing in this case is you're using the tangent line to see if I go 0.01 away from 1, how far am I going away from 38? But I'm not using the curve, I'm using the tangent line to approximate that change. Alright? And so all you do is it's going to be dy is equal to f prime of x dx, and all I do is take the derivative, so dy is equal to f prime of x, which is, what's f prime of x? 5x to the fourth plus 37. And dx, you actually have a value now, which is 0.01. Okay? And for x equals 1, you plug in 1 into the derivative, which gives you 42, right? So y equals 42 times 0.01 until you get 0.42. So if I use the tangent line to approximate the change in y, I would come up with 0.42.
So at 0.138, it's changing, like the slope is 0.42, or?
No, not the slope, the value of the function.
Oh.
The value, no,
I thought that was
not the value, the change in y, okay? The change in y is approximately,
but
when-
not in relation to x. Because if it was dy dx, it's not slope.
right,
But
okay?
it's just the change in y.
The change in y. Isn't that 0.42? dx is 0.01, right? F prime of x is 42. I plug in 1 into the derivative, right? And I get that change. How does that compare? What?
Where is it plugging 1 in?
5 times 1 to the fourth plus 37. This is the derivative of this, right?
So it's just saying,
Okay?
you move over 0.01.
Right.
Because up 0.42.
Yes. If you go over 0.01, then you would go up 0.42. So, yeah.
Hey, Mr.
What?
Change the plug-in,
Yeah, but couldn't do it by hand. Maybe you could. But this is just using the derivative to approximate it. Yeah, you could, but again, it's something that I guess they used in the olden days that we don't have to do now because we have track and calculator. But to find the actual change, I could go, if I have my function in my calculator, I don't want to do it, but, I could. Let's just show you, okay? So, if I did x raised to the 5th power, okay, plus 37x, okay, and I want to go second quit, and if I go bars, So the way I would find the actual change is by taking f of 1.01, right? So I'm going to do y bars. You could do it like this. y1 of 1.01 minus bars, y bars of 1 I should get something close to, if I did this correctly, 0.42. Okay? So by using the tangent line, I'm off by about 1,000, okay, instead of using the actual function. Yes, sir.
Can you just go back to the window of the y equals on the calculator?
I just plugged in the function.
Just the one function?
Just the
Okay.
function, yeah, and I was just trying to find the actual change in the function versus the approximate change using the derivative.
So you did y of 0.01 minus y of 1, correct?
Right.
Okay.
Okay?
Well, that would be 1
So-
minus the 0.01.
That'd be 1.01 since the
Oh,
head minus.
1.01.
Yeah.
Yeah, minus the y.
yeah.
Okay.
So, next thing, oh, I talked about that already. What am I doing here? 4 plus 3x squared, very nice. So, then they talked about this idea of the absolute change versus the estimated change, and that's kind of what I just talked about right there. This was the actual change, f of a plus dx, so if I plug in that 1.01 into my function, minus f of 1, that's equal to the actual change. This is the estimated change up there, okay? To find the relative change, that's the change with respect to the value of the function, and that will come out to be a decimal number. So f of a is the value of the function of that point, because you're trying to see what decimal part it changes by. If you multiply that number by 100, I would get the percent change. Okay, so this is delta f is what part of the value of the function. So if it's changing by 0.42 and the value of the function at that point is 38, then that is 0.42 divided by 38, which is, I don't know what that is, like 0.05 or something, so it would be like 5%. Okay? Do you want me to do this one to estimate the absolute change, relative change, or percentage change? You can do that. That's just plug in. So you would have to use the formula for the circumference of a circle, which is c equals 2 pi r. But it's just plugging into these formulas. The next thing, I went too fast on that. I got to talk about Newton's method. Maybe I'll come back to these. Can I talk about Newton's method?
Yeah.
Now, if it's cool,
Is it cool?
He's cool. Can we do it without?
We're here, I hear you. Every time you say it,
okay. So, I think you're going to have to look in the book a little bit to figure out some of that other stuff, but Newton's method is a numerical technique for approximating a zero, and so Newton's method is a BC topic which I have to teach to you, okay? So it seems like kind of a pain in the neck, but what it is you have, then there's a point, I got a text message, okay? So, for any function, so this is some function over here. For any function, you want to figure out, you want to figure out what the zero of that function is. Well, now we have kind of algebraic methods like the quadratic formula, and we have graph and calculators that can figure it out. But your calculator is actually using Newton's method in a lot of cases to figure out, to find that zero. Because you know how your calculators can find zeros? Say, oh, we have calculators, but someone's got to write the programs for the calculators to teach you how to do that. So what Newton's method says, if you have some curve and you're looking at it and you see that it crosses the x-axis somewhere, or you guess somewhere that it crosses the x-axis. So this is my point where my graph crosses the x-axis, and I looked at my calculator and said, oh, I'm guessing that it crosses at like like 1.5 or something like that. I'm guessing that this value is 1.5. Well, unless you have a graphing calculator that tells you exactly what that value is, you don't have that exact value. So what Newton's method does, it takes this value, it finds the equation of the tangent line at that value, and it gives you back a point where that tangent line would intersect the x-axis. Okay? Then what it does is it takes that point and it finds the equation of the tangent line at that point. So if I were to draw in another tangent line right here, okay, do you see that I'm getting closer to the actual zero? Yes? Then what it does, it takes that point right here, okay, and it plugs it in, and it finds the equation of the tangent line at that x value, okay? And as you can see, I get very, very close to the actual place where that curve has a zero. Yep. What?
Can't just plug in zero.
No, because that, yeah, Newton's method is the way for, I'll show you a way to do it on the calculator, which makes it pretty fast, okay? So you keep plugging in numbers until you get to a number that doesn't change by much. Okay, so this would be like the starting value. This would be x of 1. This would be like x of 2, x of 3, and by x of 3 you should be getting pretty close to the actual zero of that function. And the formula that you use is this one right here. Okay? And so, whoops. And all this, and I tried to figure out where this formula comes from, as I was tired last night. And this formula just comes from, this is the equation of the tangent line when y equals 0. Okay? And then you solve that for x, you solve it for the next x value. So you don't have to know where it comes from, you just have to know how to use it. Alright? So, let me give you an example of a problem, and I'll show you how to do it with your calculator in a minute. So let's copy this to a new page. Edit, copy, and I'm going to go new page, here. There we go. So, they're going to give you an example or problems that look like this, which say, where did it go? Wanna let me write? Use Newton's method, at Newton. I know. Long time. To find the zeros. Equals x cubed plus 3x plus 1. Okay? So, the first thing you want to do is, it says, get the first approximation to the solution of the equation f of x equals 0, graph of y because f of x might help. So you have no clue where this thing has a 0. And I don't think you could find a 0 algebraically. I guess you could approximate it using like all these rules that you learn in pre-calc, like I don't know if you remember, there's Descartes' rule of signs and other stuff that you could use. So if I take, so it's like you're using a graphing calculator anyway, why not just use a graphing calculator? Well, you use your calculator to find a starting value, but we're not going to use the second calc 0. Okay? I'll get there. Alright, so if I were to graph, that's not the function I want to graph. So I want to graph x raised to the third plus 3x plus 1. okay? And if I graph, I see this function. I zoomed out a little bit, but it goes up. If I zoom out, I would see more of the function. Zoom out, wait.
That's a window.
Now I just said a normal window. -10. It was like from -5 up to 5. Okay? Where does it appear that this thing crosses about? Negative, we could try. Negative point, okay, so Logan says it's negative. Say I did choose -0.5. Let's just choose that, okay? So I'm going to guess that it's right there and see what happens. So we're going to start at x equals -0.5. Because that's what Braden said to choose, and you get it, all right? In the book they say choose -0.3, but as long as I do enough iterations, okay, I'm finally going to get to the 0 of that function, okay?
Yeah.
And so let's guess that the 0 is at -0.5. So what I want to do is I'm using this formula, so x of n, that's my starting value, -0.5 plus minus f of -0.5 over, minus sign is out there, over f prime of -0.5. And then I want to get that value out, and that value that I get out is going to be called x sub n plus 1. Alright? And I can do it, let's just find f prime of x. What's f prime of x? What's f prime of x? 3x squared plus 3. Alright, so they have a couple in your homework there. They ask you to do this by hand, where they start with a nice even number, and it comes out. But I'm going to show you how to do this on your calculator really quick. First thing you do is you stow. First you have to quit, okay? First I have to put in my derivative into y2. Okay, so I'm going to come over here. I'm going to put my derivative equation into y2. 3x squared plus 3. Alright? There's your derivative equation. Yes? No? Yeah. So, now I'm going to go second quit. And I'm going to store -0.5 as x. Whoops. I screwed up. Okay. I'm going to store, sorry. First I have to hit -0.5. Clear. I missed. So I'm going to put in -0.5 and store that as x. Alright?
Alpha x.
Just x.
You can do that.
Yep, you can do that. You don't need alpha. Okay? And now what I'm going to do is I'm going to go x, I'm going to go use this formula. I'm going to go x minus, and I didn't know you could do this either, bars, sorry. Let me try this again. Yeah, that's right. X minus bars, y bars, function, y1, divided by bars, y bars, function, y2. Okay, so I'm just using this formula right here. X minus f of x over f prime of x. And I'm going to store that now as x. Okay? So what that's doing is taking my original x value, it's plugging it into the function divided by its derivative, and it's storing that as the output. Okay? So if I hit enter, hopefully this gives me something close to, it tells me that, that gives me -0.33. Okay, so that's pretty close to the 0. But if I want to find the second iteration, I don't have to do anything other than hit enter again. And it gives me this. Okay? And if I want to find the third iteration, I go like that. You see how this number is getting closer and closer and closer to some value?
We didn't have to store that?
No, you just keep hitting enter. Because it's taking that output and it's putting it back in for x. Okay? I mean, if you wanted to do it by hand, you would have to plug f of negative point. What your calculator's doing is taking negative 0.5, it's plugging in here, and then it's taking negative 0.5 and plugging in here, and then it's dividing them and subtracting that answer from negative 0.5 and giving an output. And it's taking that output, right, and plugging that output back in here and here and giving out another answer. So what it's doing on your curve, you know, here's your curve, it's finding, so we guessed it was negative 0.5. Said, oh, that's not it. But, so the tangent line right there is something like that, right? Wait, what am I trying to find? I'm trying to find the zero. And I said, no, that's wrong, it's more like over here. And it's going like this, and it's going like this, and it's going like that. Anyway, it's getting closer and closer. If I keep hitting enter, you see that eventually this number is getting closer and closer to a limit. And when those things stop changing, that's when you reach the zero of your function. It doesn't matter if you start in front or behind, as long as you don't start too far in front. Oh, so I guess I started. Yeah, that's kind of. So what do they do? Yeah, I guess it doesn't matter if you start in front or behind. But beware. They have some bewares. Okay? Because
It was really weird. It went to negative 0.2 at the first thing, and then it
really? Because